tell me this. This is, by the way, we're starting 1-2 about functions. Oh. So we're talking about functions and their properties. So I guess before we start, we need to define what a function is. Jackson, what's a function?
Function and property?
No, what is a function?
Oh, a function is two things that make it variable.
Ooh. We'll work on that a little bit. Jerome, you know what a function is?
I'll be like, instead of
Well, I do appreciate your honesty. So, you don't remember? That's okay. That's all right. Does anybody remember what a function is?
Is that an input-output?
It is an input-output kind of thing, but it's a special input-output kind of thing. So it's a relationship or a relation that, what do you mean by input-output? What does input-output mean?
Like, if you input something,
You get an output, you get a y. For every x, there's a y, right? So it's a relation that for every input, there is one output. So I'm going to say x is my input, y is my output. Okay? So graphically what this means, and if you think about it, every single x value, if I put this on an xy plane here, every single x only has one y that corresponds to it. If I come over here when x is 1, there's only one y value that goes with it, right? There's not another y way down here that's part of the graph. That graph only has one y value when x is 1. Does that make sense? There's never any place on that graph where it has more than one. But if I turn that graph on its side, and I put my same x and y here, well, now when x is 1, how many outputs do I have? 1, 2, 3. Because there's more than one, this one is not a function. Okay? So function,
it's one
y for every x. So this x is 1, but it has this y, and this y.
those aren't on the y.
But they have, what I'm saying is corresponding. So this might be 1, 1, this might be 1, 4, and this might be 1, negative 2. It's the same x value, but it has different y's that go with it. You see what I'm saying? And when x is 1, okay, so, right. So here's a simple little test we use to do it, and this will make sense whenever you see it, I hope. And I hope you've done it before. You don't even know what it is. If we have a graph, we can use what we call the vertical line test to check functionality. So let's look at those same two graphs. I had a little cubic. I don't remember which way it was going. It doesn't matter. Then I had this little crazy cubic on its side. Okay. Vertical line test says if you take a vertical line anywhere on that graph and it intersects more than once, then it fails. So if you took your pencil and you run across, if it ever touches more than one time, it fails, okay? This one passes. Are you kidding me? I was helping my nephew in 9th grade in Algebra 1 with this last weekend. Y'all never saw this? Okay. So look, that's okay because we'll try that now. If I take a vertical line and I run it, is it ever going to hit the graph more than one time? A stationary vertical line. Is there ever one vertical line that will intersect more than once? I'm just running it across here.
I thought vertical was like.
It is. That's why I'm holding my pen like this. See?
Wait, what do you mean?
The pen is the line. The pen is the line.
You probably circle the line.
Okay. The pen is the line. Let me show you one. Let's look at this one first. Do you see if I come with a vertical line here? 1, 2, 3 times, fail. Right? Fail, not a function. There's never any place I could put a vertical line, though, here, that would touch more than one time. You see what I'm saying?
Okay, I'm still confused why it's
Will the yellow line ever hit the green line more than one time? Will it ever intersect more than one time in the first one?
No.
Is there anywhere you could put a line up and down where it would hit it more than once?
Yeah, I did understand.
Like that?
Like this one, see? This one will. It hits twice. I mean, it hits 3 times.
Oh, so
this one doesn't.
Okay, so.
Okay. It's the same concept as there's not y's that go with the same x. It's just a quick little test. Let me show you a couple more. Don't blurt it out for those who are struggling. Strawberry what, Jerome? Strawberry functions?
No, a strawberry lollipop that I'm about to eat while we lollipop.
Lord Jesus, take the wheel. Okay.
No, I do that. No, I do that. Because he don't leave for a lot.
I don't even know what you're talking about right now.
You
Yeah.
said, Lord Jesus, take it. He don't leave for a lot.
She
did not say that.
Yes.
You can't take my word.
If it hits more than once. Okay, let me show you. If it hits more than once, it fails. If it only hits once, it passes. Yep. It can hit one time, but it can't hit more than one time. Yes. That's the test to see if it's a function. It either, yes, it is a function, no, it's not a function. Okay? 2 more. Actually, I lied. Let's do 3 more.
All right, so wait.
One of them is not like the others. One of these things is not like the others. What? Okay, what else? Which one's a function, which one is not?
No, the line right there, that one, those are functions.
Okay, so first one. Raise your hand if you think the first one's a function. Yay, y'all are right. It's a function because anywhere I put a line, it's always only going to hit one time. Yes, this is a function. How about the one on its side here at the bottom? Function or no? No, I'm hearing a consensus of no. I'm seeing lots of heads shaking. No, because if I put a line, 2 times. So fails. You fail. Okay, how about the last one? It's a function. It's a function. Do you see what we're doing? You can take your pencil if it's there and run it just across to see, is it a function, is it not a function? Does that make sense?
Yeah.
Okay. This is definitely not all. This is probably the longest section you've ever seen in your life. We're going to take at least 2 days doing this section, but this is just a piece of it. All right, so speaking of functions, you are used to seeing things like this, right? What does this look like when you graph it? A parabola. This is standard form of a quadratic. When you graph it, it looks like this, right? Is that a function? Why? It passes the vertical line test, right? So, To show that it's a function, to denote that it's a function, we use something called function notation, and I hope you have seen this at some point. You say that before you've even seen it. This is called function.
Wait, does it count when they say G?
Yes. That's just different ways of naming them, but it's the same thing. It tells me, hey, what you got coming up here is a function. Anything you plug in for x, it's only going to have one y. It is a function. Okay? We read this as f, anybody know, of x. Have y'all seen that before? Nope. Yes, yes, nope. Okay. Somebody asked, is that the same thing as G and H and everything else? It absolutely is. As we start working with functions, we name them. It's kind of like y'all having different names so we can distinguish between you. We name our functions different names so that we can distinguish amongst them. So you might have, if we're comparing functions, you might have an f of x, a g of x, and an h of x so that you can go back and refer to them by their name. Okay? It's just a way of naming them, calling them something different, okay? But it still tells us that everything, that it's a function. What follows is a function. Does that make sense? Okay. I promise we're going to get to the algebraic part in just a minute. What you need to understand, your big takeaway from function notation. First of all, this does not mean multiply. This is not f times x, okay? Never think that. This is telling you x is my input. F of x altogether, in other words, what I get when I plug in is my output. So the point x, y can also be described as x f of x. Because y is the same thing as f of x, okay? Those are used interchangeably. Everybody okay on that? It's just a fancy way of writing it. Looks a little bit different. Yes. And it lets us know, the name lets us know that it's a function. Everybody good? What if I gave you this? So y'all all got this page? So we've got f of x equals x squared plus 2x, that same function. And I said, what is f of 2? Find f of 2. What does that mean you do? You plug 2 in for every x. So whatever is in here is what's replacing the x, right? So 2 squared plus 2 times 2 plus 3. Okay? Remember that first test we did? I said, what's the value of y if x is whatever? This is the same thing. It's just asking you in a different way. So we get 4 plus 4 plus 3. 11. So f of 2 is 11. Does that make sense? I'm sorry, I didn't hear you. I'm sorry. All right, that's function notation. If y'all are good with that, I want to make sure that I give it to you the way your book does. How about this? If I said that y equals x squared, define y as a function of x. What does that mean? Define y as a function of x. It is. It's something equals x squared. How do I tell you that it's a function? F of x. I define y as being f of x equals x squared. All right, let's do domain and range. Oh, domain and range. You should have been pounded with domain and range since like the 8th grade. Do not tell me you don't know what domain and range is, because I might just cry right now.
Wait, what's
All right, domain and range. What does domain mean? Or what does domain describe? Oh my goodness.
It's like adding all of them up. And like dividing by like whatever it is. That's something else.
All right, now, I guess I'll just tell you instead of us just guessing. Domain is a culmination of all your inputs. What is my input in a graph? The what? The x. All values that x can be. Okay? Domain describes x. So what do you think range describes? The y. It's your output or your y. But the thing is, it's all the values that they could be for that function or for that graph. Okay? So anything that it could be is your, anything that y can be is your range, anything that x can be is your domain. We're going to describe this in interval notation. Y'all get real excited. You've already tested on that. I showed you that. With the brackets and parentheses and infinities. All right, before we do it algebraically, let me show you a couple graphs. Let's do the domain and range on them. Because we kind of have to think through some of these. All right, I know. Think through them. Today you will be graphing and doing things. Pretend like that's at 0, 0. If I'm looking at this, now if domain is all the x values, then that's left to right on your graph. Okay, so as I look at this parabola, left to right, is there anything that x cannot be? Is there any time that you could come and say, okay, if I'm right here, is there a y value that goes with it? It might be way, 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 way up, right? But there's one there. Is there ever any time when there's no x value left to right? No. It can be anything. Do we all agree? If this was the graph y equals x squared, you could plug anything in for x and it would give you a corresponding y value, right? Are we all in agreement? Do y'all understand what I'm saying? Some of y'all are zoning on me. Okay. So the domain then, when there are no restrictions, nothing holding it back, and it can be anything in the whole wide world. How do you say that in interval notation? Anything in the whole wide world. Any real number. Negative infinity to infinity. Remember, when I'm in interval notation, I want to make sure I go from smallest to biggest. Infinities always get parentheses. When I include a number, it gets a bracket. All right, the range here. The smallest value, I'm going bottoms up here, okay? So the smallest y value that you could ever have on this graph is 0. Does it get a bracket or a parenthesis? Why? There's actually a point there, right? That is a point. It is included on the graph. So from the bottom up, what does it go up to? Infinity. That's right.
So wait. Okay, exactly what we started. So infinities are
Always.
and then the numbers are brackets.
Yes. Well, the numbers are bracketed as long as there's a point there. All right, let's look at another one. First of all, function or not?
Yes, sir, yes, a function.
Why, Jerome? Why is that a function?
Because if you put a vertical line through, it only goes through once.
Good job.
Yes, sir, John.
So we know it's a function. What's the domain of the function? Too far, too much.
Negative infinity.
You're correct, Jackson. You are correct. You're good, but you gotta say the smallest one first.
-1.
Good job.
Put a bracket under it.
Why, Jackson? Why is it -1? It is a bracket.
Because that's what it.
The lowest it ever goes is -1, and then it goes up to 1, and it never goes past it.
Yeah.
Okay, let's see how good you really are. I'm sorry. Let me go back, and I'll pause the video and let you. Hey, let me show you one to see if you really understand. This one, it gets fun, right? Is it a function?
No,
Why?
because you put it through the little thing, so go.
It fails the vertical line test, right? Not a function. But I can still do domain and range on this not a function. I can. I certainly can. So not a function.
But the domain would be a distance negative infinity,
Yes.
and the range is -1 to 2.
You're telling me that there's only graph between -1 and 2. Is that true? Okay, so yes. But what you're telling, if you say that the range is from -1 to 2, you're telling me that there's only graph between -1 and 2.
Oh, no.
Might be negative.
Gotta use a U.
Smart.
What's the lowest the graph goes? Bottoms up. Negative infinity. And then it goes up until it hits what?
1.
1, and it stops, right? At -1, it stops. That's right. Then it doesn't pick back up until you hit what? 2, and then it goes up forever. I told you I was going to test you.
So, what I'm not getting is, how do you find if infinity or not?
If it goes on forever. Okay, so domain, we're going to do domain mostly algebraically. You'll look at the equation to tell the domain. Most of them are going to be negative infinity to infinity. If you ever go anywhere on X and there's not a Y that goes with it, then it's restricted. But most of the time, in other words, if I come here, is there a Y somewhere that will go with that? Yeah. If I come down here, is there ever any place where you couldn't get a Y with your X? So it's negative infinity to infinity. Left to right.
What is that in between?
A U. It joins the two pieces together.
So wait, if it had like, dots at the end after arrows, then it would be a number?
Yes, yes. All of ours are going to be arrows though.
So does it matter if you put -1, -3, or can you like?
You have to go from smallest to biggest. So you have to go from negative infinity to -1. You can't do them backwards. Well, it will be, and you're going to graph them, but then we're also
Are we getting the
with your calculator, not by hand.
Can we get the domain? Or do you have to find that?
You got to find that too.
So I got the bottom one, where it's negative infinity, because it's -1 and 3. So where you get to.
Because then there's no graph here, and the graph doesn't pick back up until I hit here. So that's where the 2 comes from.
So that would be, that's just 2.
2 up to infinity. All right, let's look at domain algebraically. All right, so this is new stuff probably for you. You may have done domain and range looking at a graph, but I doubt you've done domain algebraically yet. So you graphed a lot of things in Algebra 2, or you should have. You graphed things like radicals. You graphed things like fractions. You graphed quadratics. You should have graphed logarithms. I don't know if everybody got to that. You graph lots of different things, right? So there are times when our domain is restricted based on the function that we have. Okay, so there's two main things you're going to look for when we start talking about, because remember domain is x, so we're looking at what x can't be. Hope if you'll put that away, please, ma'am. We're looking for two things. We're looking for radicals, and we will expand this as we move on. But for right now, we're looking at radicals and fractions because we're talking about what x can't be, okay? When x is restricted or when there's things that, that can't happen. So think about radicals for a second and why that might be something that I look at. What can you never have with a radical? A negative, right? So if I'm graphing and I have something like the square root of x, I know that whatever's under here can't be negative, right? No. So that's one thing that's going to restrict my domain, okay? So what I'm going to have to do is I'm going to have to take what's under the radical and make sure it stays positive, all right? We'll break these both out in just a second. I'm just kind of giving you an overview right now. So then fractions, if I have all these fractions, whatever, what can never happen with a fraction? Okay, you're thinking exponents. Keep going. Keep thinking of things that you can't have in a fraction. Specifically about the bottom. What's true about the bottom of a fraction? This is the numerator, this is the denominator. What's true? Yes. Good job, Jerome. I'm impressed.
Yes, sir.
It can never be 0. He's just going to make rounds from the room, so. So we're going to have to leave that out of our domain when we do it, okay? So let's look a little closer at these two scenarios, and I promise I'm almost done. I'm going to stop with domain and range today because I think it's enough for one day, and we'll pick up tomorrow with some more. But we do need to graph and look at some things. All right, let's talk about radicals first. Radicals. If I have f of x equals the square root of x plus 2. And I'm asked to find the domain and range of this function. Okay, how do I know it's a function? F of x tells me it's a function. I don't even have to check to see if it's a function because if it tells me f of x, I know it's a function. That's right. If I graph it, it'll pass the vertical line test. Okay. So as I look at this to find the domain, here's the way we do domain. We always assume domain is negative infinity to infinity, and then we look at what it can't be, okay? Or we look at what we know it has to be. So for this one, I know that this has to be what? What's under the square root? It has to be what? Starts with a P, positive, right? So what we're going to do is we're going to take what's under the radical and make it greater than or equal to 0 because that's how I make it positive. Okay? So x can be anything in the world as long as it's bigger than or equal to 0, right?
Yeah.
And since I'm describing domain and domain is x, then if I describe this, I've also described the domain. So if x plus 2 is greater than or equal to 0, What do you know about x? Greater than or equal to what? Solve it for x, -2. Right? Describe that in interval notation.
Okay, so it would be negative 2 infinity.
Come on. This is my domain. Now to graph it, to do the range, I need to graph it, okay? I'm not going to make you graph these by hand just yet. If you take out your calculator and you do the square root of x plus 2, now make sure, see how my parentheses are doing around that radical part? I need to make sure that I keep all that way so that it all stays under the radical. And I'm going to do a zoom 6 on it, so I do a zoom, 10 by 10. Oh, square root of x plus 2. Y equals, yep. Second, x squared. Okay. So now I've got the square root of x plus 2. I hit my zoom 6, and this is what my graph looks like. Does my domain match my graph? On my graph, is x bigger than or equal to 2, to -2? Does x left to right, it starts here. It starts here at -2, right? And then it goes on forever to the right. So I'm good there, right? My domain justifies graphically. How about the range looking at this, though? Bottoms up. Where does it look like it starts on Y? It's actually on that point. Huh? You can zoom in if you want. What you can also do, since we know it goes over to -2, if you hit second graph at -2, what's the value of Y? Okay. That tells me that this point right here is -2, 0. So what's the range? Come on, y'all can do this. What's the range? Y is the range. It's 0. What's the lowest the graph goes? I'm sorry I didn't hear you yell at me or do this or something. 0, right? Up to what? Infinity. It's creeping up as it goes. With a parenthesis. The range is from 0 to infinity. Because the graph did this. It went from -2, this was the point -2, 0, and it went like this. So the smallest it can be is 0 up to infinity. You okay? Okay. We told you that when you walked in.
I got one of my walls.
Say again, Cameron.
So, okay, so the lowest was -2, 1. You always take the lowest out of the two numbers?
No, you take the Y back. Range is Y. So this is Y. I can't write on it.
So you always take Y?
Always Y for range, yes. Always X for domain. You see this is -2, 0. So -2 was the X side, 0 was the Y.
And that one was...
One more radical one. I want the domain and range of this function, and I want you to find the domain algebraically, justify it graphically, and find the range graphically. That is the exact same thing we just did. I'm just putting it in words out there. It sounds like more than what it is. All right, domain and range. Graphically for both. Domain, I want you to do algebraically as well. So I need a graph, and I need to sketch a graph to justify graphically. And then I need also algebraically for the range, okay? I mean for the domain. So remember, I'm looking for one of two scenarios. I'm looking for a radical or a fraction, or both. And in this case, I have radical, right? So this is the only thing that's going to restrict my function. What do I need to do with it? How? How do you force it positive?
Oh, you got it.
Somebody said it. Greater than or equal to 0. That's going to ensure I'm always positive, 0 or bigger. You can do the square root of 0, but you can't do the square root of -1. So if I solve this for x, my goodness. If I solve this for x, what do I get? X is what? Greater than or equal to. Write that in interval notation. Close. X is bigger than 1. So the smallest it can be is 1, and then infinity. Okay, this is my domain. I'm going to graph it.
So, you take the radical
And that's your domain. But you turn it into interval notation by making it greater than or equal to 0.
So we have to equal it.
You have to do that because that's making sure it's positive. Square root of x minus 1, and then outside the parentheses is plus 3. Do it. When I graph, is the domain, does that look correct for the domain? Is it bigger than 1 from 1 on? Yes. Because it starts at that point. It starts at that point, and then it just kind of goes up and over. So I need to know that y point, right? How might I do that? Second graph. What point? What's the x point there? 1. I need to know what y is there, and it's what? It's 3. Positive 3, right? That's telling me that on my graph, this point is 1, 3. And it does that. Why is what? It's just part of the equation. We'll get to function transformations. We'll get to what that does later. But it shrinks or stretches the function. It makes it taller or skinnier. What's the range then on this graph? 3 to infinity. All right, last scenario.
Wait, so the starting point for the whatever, that's going to be the x will be your domain, and then the y will be your
Yeah, for these, for radical functions, yes. Yes. All right, scenario number 2. Fractions. And we said what can't happen? 0 can't be on the bottom. So for this one, we're going to make the bottom 0 to see hey, this is what happens if it's 0. We're going to find this so that we know what x can't be. Okay? So we make the bottom equal to 0, we solve, and we leave that out of the domain. So same scenario, same thing. Find the domain and range of the function. Justify algebraically and graphically. Okay? So, what can x never be in this equation? 0, right? This is easy because the bottom is just x. So I know that x can't be 0. How can I write a domain that says everything in the world except 0? You might not know this. You might not have grasped interval notation well enough to say this. Go to negative infinity, get to 0 and stop. Don't include 0. How do I say don't include it? No. Come on, close, parenthesis. Parenthesis says get really close to it, but don't touch it, right? And then pick back up on the other side of 0 and keep going forever. To leave just one number out of your domain, you do back to back with the same number with a U, okay? That says get really close to it from either side, but don't actually touch it, okay? And then for the range, I need to graph. Now, this is going to look like a funky graph because it is. I'm going to do y equals 2 over x. Okay. Remember what we said. What can x not be? 0. So look at what the graph is doing. Left to right. We're not looking up and down yet. We'll get to that. But left to right. It's getting really close to 0 from that side, but it's never crossing over the axis. Same thing over here. It's hugging it and getting really close, but it never actually touches. Does that make sense to you? Do you see why it doesn't have 0? Okay. So my domain for this justifies graphically. And I'm going to sketch a graph because that's what you're going to have to do for your homework. What, looking at that graph, do you think the range is? Bottoms up. What's the lowest the graph goes to? Negative infinity. Then it goes up to what? Look. 0. It's doing the same thing on the range that it's doing with the domain. Look at it. It's hugging that axis from both sides, but it's never crossing over. So it's getting really close to 0, but it's not crossing. And then it's picking back up at 0 and going on forever. Same thing.
Is that always gonna be true?
No. One more example and I'll be done. I said one more scenario and I was done. It's still the same scenario. Well, kind of, sort of. This last example, I promise. G of x for Jerome. Garone. I know, I'm picking. It's muggy, not gummy. I'm looking for problem areas, right? So I can establish my domain. So there's 2 problems here, right? What's one of the 2 problems? The radical. What has to happen with the radical? What has to happen with the radical? Come on, y'all. Yes. Whatever's under the radical has to be bigger than or equal to 0. What's another problem? X minus 5 cannot be 0, right? So what can x not be? So think about this on a number line, okay? And if that helps you, sometimes when I have double scenarios here, I have to think about it on a number line. If x is bigger than or equal to 0, so I'm right here, I'm bigger than or equal to 0, right? But wait, because when I hit 5, I got to leave that out. So anything bigger than 0 except 5. How do I say that in interval notation? Look at your number line. What's the smallest x can be? 0. Is it a bracket or parenthesis? It goes up to what? 5. How do I leave out a number in interval notation? Double parentheses with a U, right? Because this had both scenarios in here. This had the radical, which means it had to be bigger than this. I got two different parts but I have to make them into one. Okay? Now, if this had said x cannot be -5, and -5 is over here, well, bigger than 0 would take care of that. You wouldn't have to include it twice. But because it was in my domain, I did have to include it. How about the range? How do you know it's the same thing? But I told you that's not always the case. So you better graph it. It probably looks kind of funky. Ooh. X is bigger than 0. And it leaves out 5. It hugs 5 from both sides. So that justifies graphically. So if I sketch a graph, my pen slipped. It's going to look something like that. So what is my range here? It's the lowest it goes. -infinity up to what? Yeah, it goes up to 0. Does it include 0? Look at it. No, it's not touching 0 there, right? It's hugging it. Picks up. No, don't relate domain to the range. Don't relate those two. You're going to look at it graphically for the range. We'll talk tomorrow. We'll talk about asymptotes and how to find those and how they impact domain and range. For right now, I just want you to look graphically. Okay. So for your homework today.